Now we go to another function, and the other function is the expansion with the help of Taylor series for sine of x and cos of x. So let's see that if I want to write sine of x, like sine x, okay, then let's write this one as sine x, and this is equal, according to this expansion, when expanding this one with the help of Taylor series, we will have x minus x cubed by 3 factorial plus x5 by 5 factorial minus x7 by 7 factorial and plus so on. And the nth term I will have is this is equal to summation on n and minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 factorial. Now we want to see that, and the approximation in this series is that sine of x for x very small, sine of x goes to what? This we will see now in the plot, that to what it is going when x is very small. When x is almost less than 0.5, then we are having the two values, the two functions is the same. Let's plot the second term. Now if we plot the second term, then it is completely different. Like this goes like this, x cubed by 6, and the next term will be even much farther than that one. This is the next term, which is x5 by 150. But now look at the addition of the terms. So the addition of the terms are, let's say I'm just adding the first two terms in this expansion, which is x minus x cubed by 3 factorial. And if I plot this one, you can see how closely they are matching. And if I add the third term in this expansion, then you can see. Now the third term is the green term. You see that the two functions from minus 2 to plus 2 are almost the same. So as I will be increasing the number of terms in this one, then I will match all the sine function. So the polynomials are actually point by point, they are then taking the shape of the same function. Clear? We will have to write one thing, that sine of x almost goes to x. So here sine of x almost goes to x for x very small. And you can see here that sine of x is almost going to x when x is very small. I can zoom this one and you can see that the two are almost the same for small values of x. Now let's start with cos x. For cos x, I know that if I expand the cos x with the help of Taylor series, then cos x is equal to 1 minus x squared by 2 factorial plus x4 by 4 factorial minus x6 by 6 factorial and so on. And the nth term I can write summation on n runs from 0 to infinity and minus 1 to the power n, and x to the power 2n divided by 2n factorial. Now the first term in this one is 1, and then x square by 2 factorial, x4 by 4 factorial, and so on. So if x will be very, very small, then cos of x will be approximately equal to what? We will check this one. And the very first thing, let's plot cos x, and this is cos x, which is plotted. So let me reduce the scale here, and this is cos x. So cos x we have plotted, and okay, let me reduce the scale. So this one, let me move it down. Okay, now cos x is equal to, let's say, the very first term, which is 1, and then x square by 2 factorial, so it's completely different from that. Then x4 by 24 means x4 by 4 factorial. So we are having the functions like this, the individual functions. But now if we just add the two terms from this expansion, which is f of x equals 1 minus x square by 2 factorial, these are the two first terms. So let's see. When I plot 1 minus x square by 2 factorial, you can see that it is now taking the shape of the cos function. Similarly, another term, and another term will add up, means now this one is copying the same or behaving the same as up to here. If I add the fourth term, then I will have the matching till this point, and so on. So if I increase the number of terms, I will get almost the same function. In order to 100% get the same function, we will have to go for infinite number of terms, and then it will be the function, the same function will be reproduced. Okay, one thing more here, that we will have to follow the mathematics, that how mathematics actually follows the, means what is the way of mathematics. For example, if I say that where is this point? Where is this point? Let's say this is a point which is in the x and y coordinates. This is the x coordinate and this is the y coordinate. If I ask this thing, that where is point A, then I will say that go this many points along x and then go this many points along y, means go first from the origin to x this many points, and then from the x go this many points along y, and you will have this point xy. So how the mathematics actually do like this? This is the geometry that we did. Mathematics says that there is a point, let's say this is point A, and consider, means mathematics will always says that let us suppose point B. It will always suppose any point B somewhere, and it will say that move point B when point A will go close to point A, or you can say when the difference between these two will go to 0, then this will be actually point A. So mathematics will move point B towards A, and it will tell you that when the difference between them is exactly 0, then it is point A. But exact 0 is not possible. So it will always be going to 0. For example, if this point I have exaggerated a little bit more, this point I have exaggerated here means a big dot. But if it is a normal dot and I put another dot exactly over it, and then I observe the two in a magnifying glass, then I will find that the two are not exactly overlapping each other. They will be a little bit separate. So what I did, I just magnified it. Means I went to more number of terms. And if I will see the same thing in a microscope, then these 2 points may be very far apart from each other. And if I see this in a scanning electron microscope, then they may be very, very far apart from each other. So I will go closer to 0. The more I go closer to 0, I will be exactly at point A. But it depends how much accuracy we need. So the mathematics approach is always very accurate. One cannot achieve exact 0. So that's why when we expand the function, then we see that up to how many polynomials we go, we will get this function. So it always depends how much accuracy we need. The more accuracy we need, the more terms we will go. Less accuracy we need, then we just approximate this function. Like we approximated that e to the power x is approximately 1 plus x if x is very, very small. Sine x approximately goes to x if x is very, very small. So this is approximately x when x is going to be very, very small. Cos x approximately goes to 1 when x is very, very small. We use these approximation in physics a lot, because you know that when you calculate the simple pendulum equation, the equation for time period or frequency, you consider over there that sine x is approximately x, sine of theta is approximately theta when theta is very, very small. So if I give to the pendulum more amplitude, now in this more amplitude, theta is no more very, very small. So the calculation that means the time period that I will measure with the help of stopwatch will be different from my equation, because in my equation I have used some approximation, then I have derived that equation. They will never match. But if I will keep the amplitude very, very small, then the stopwatch calculation or the stopwatch measurement will match my theoretical calculation. Because the theoretical calculation means the equation is after some approximation. Like I write that this is T is L over G square root and some constant term there. So that is after approximation. It was this approximation which was adopted. All of physics we are having approximations because we cannot calculate the n number of terms.